0000 on the atomic clock. Okay, if we can come to attention. It's my pleasure to welcome back Jim Gates. I say welcome back because those of you may remember that Jim gave the CFA colloquium in 2016 on a somewhat different topic, but related to his area of research, which is supersymmetry, supergravity, and superstring theory. And forgive me if I read because the list of credentials is long, but I'll get through it quickly. Jim received his bachelor's degree from MIT in 2 subjects, mathematics and physics, and then in 1977, a PhD from there. Jim is currently the Ford Foundation Professor of Physics at Brown University and Director of their Theoretical Physics Center. When he joined us in 2016, Jim was the Regents Professor at the University of Maryland. He went to Brown, I think it was in 2017. Yeah. Jim served on the President's Council of Advisors on Science and Technology under the Obama administration and was a recipient of the National Medal of Science in 2013, as well as being elected to the National Academy of Sciences in that same year. Jim is currently the president-elect of the American Physical Society, a position he'll assume in 2021. If Jim looks at all familiar to some of you, it's because he's appeared numerous times in the PBS series Nova, as well as other WGBH-produced science programs. In fact, the executive producer of Nova is a mutual friend of ours, Paula Aspel, and when she learned that Jim was speaking today, she emailed me frantically to say, and I'll quote here, "If appropriate, Gary, please mention that Jim was, and I hope always will be, a treasured partner to the PBS Nova series, always finding a way to explain the complicated and difficult concepts of physics in the most elegant, clear, and compelling manner." Finally, Jim is the author, along with Kathy Pelletier, of the book Proving Einstein Right, The Daring Expeditions That Changed How We Look at the Universe. The book will be available for purchase if you're interested after the talk in the back. But the book has been reviewed by a number of people, all of whom that I saw lavished considerable praise on the book, including Walter Isaacson, the author of Einstein, His Life and Universe, Martin Rees, and Michael Turner, among others. So before I leave Jim only time to give his second 15-minute talk of the day, I'll turn things over to Jim.
Thank you for that mercifully short introduction. I quite frequently have to sit through those things where my hosts are not so kind, and they just go on, and I start to get embarrassed. And thank you. Okay, so let's get started today. Proving Einstein Right. This book is something I've wanted to do for about a decade. But because I'm an active researcher, in fact, my latest paper was posted to the archives last week, and I've got another one that will be posted probably within 5 or 10 days, and one just got accepted at JHEP, which is where I publish principally, and probably some of you know these journals. But because of my passion for doing research still, I am not a natural generator of books. And so whenever I write a book, it's because something has happened that makes my mind it becomes like an entangled photon with at least one other mind. And on this occasion, it's my co-author, Kathy Pelletier, and we're going to hear that story. So the book was written for a number of reasons. Let me go here. The science in this book is not the star. And I keep hearing people say, well, gee, why didn't you put more science in it? Well, since I'm a theoretical physicist, I don't need a novelist to help me write a science book, so I don't understand why that particular point gets raised a time. I want to write a book for my students. Why? Well, this is my 48th consecutive year teaching. First time I stepped in the classroom was 1972 to teach calculus at MIT. And I've been teaching every year since then. And I love teaching. But I've watched, as a consequence, I've also watched a couple of generations of students as they become masters of the canon that is established by people like you, the scientific knowledge that goes on and produces the foundation, the bedrock for future advances. And it has been often my perception that as this happens, many students lose confidence. And this is particularly true for underrepresented minority students, and it's also particularly true for my female students. I've seen it over and over again. So for me, the real reason I wanted to write this book was to expose what you already know, namely that scientists are people, and that we are subject to all of the pressures and the difficulties, the highs and the lows that mark being human. And so this book is really an attempt to do something that we had never quite seen done before. We focus on 8 astronomers, and I'm going to get to them. But what we tried to do in the book is to produce a document that, to the best of our ability, would be what they would have created if they had kept collectively diaries. So it is a very internal, outside-looking book, and not looking at the science, but looking at what they were feeling and what they were doing. Now, one of the amazing things about my co-author, Kathy Pelletier, is that she is a novelist. She's written novels for over 30 years, usually fiction. Some of her novels have been made into books. I'm sorry, movies. And so in my sort of dream about producing the kind of book I wanted to have, collaboration was clearly the route to go. That is, she's just a superb writer, and I actually learned a number of things in writing this book. It was a 3.5-year-long effort. During that entire time, we didn't meet face-to-face until after the book was published. And when we had our first book signing at Brown University in October was the first time we were in the room together. So let me tell you how let me let you hear how Kathy says this got started.
We're going to sell this to New York. My agent will never sell this. So I'm lying on the sofa, kind of sad one night with my hand in a bag of potato chips, thinking, what am I going to do? And this commercial came on television.
Marvin thinks you have to be a brainiac to do your own taxes. So we brought in world-renowned brainiac Dr. S. James Gates Jr. to help him get started.
Marvin, you got a W-2?
Yeah, I do.
You got a finger?
Yes.
Take the finger and press it right here. Yay, you got it.
So I thought, well, you might not have to be a genius to do your taxes, but I need a genius to co-write this book with me or it's never going to get done and it won't get sold. And so I got up and Googled S. James Gates Jr. because he looks so nice and friendly in that commercial. And sure enough, he was at the University of Maryland, and I sent an email. I sent my bio with the work I had done and what I published and said, I'd like to talk to you about a possible book. And the next morning, his assistant emailed, Professor Gates would like to talk to you.
You mentioned you typically write fiction, and you...
So that's how the book got started. Several years ago, I did a commercial for TurboTax, and you can go to YouTube and look at it if you want. It was the second commercial I've done in life. About 2 years earlier, had done a commercial for Verizon. Now, why these commercials happen, I don't know. But people ask, and I'm still crazy enough to say, yes, let me try to do something I've never done before. See if I fall on my face this time, right? But that was truly the genesis of this book. It was the fact that she saw this commercial and she wanted to write a book. She has zero training in science, but she's an accomplished writer. I have lots of training in science. I am not an accomplished writer. And so the two of us together could fill in the gaps in the others in trying to reach the goal for this book. So let's rapidly go through a little bit of science. As you all know, in 1915, Einstein gave us one of our favorite equations here. He referred to this at some point as a blunder because he couldn't decide quite about what to do with this term. We call it the cosmological constant. He started without it, then he introduced it, then he erased it. And then about 20 years ago, we put it back in the equations due to a Nobel Prize that went to the discovery of the acceleration of the universe. People like me, we're particle physicists, so we tend to think of this in an analogy to electromagnetism. And so we do things like say, well, there's this covariant derivative. The field strength of the covariant derivative is basically the Einstein curvature tensor. And what you get out of it, as you know, is you have a scientific justification for producing pictures like this. Now, I tell people that, to me, this is Einstein's greatest contribution to our species, because this gives us, the scientific community, the foundation to tell our fellow humans that 13.8 billion years ago or so, something happened that we call the Big Bang. There was a period of inflation, of dark ages, and in all these transformations of matter and energy, and at 380,000 years ago, our universe was so clever it took its own baby picture, right? We get the right to say these things now. And to me, the ability for our community to express this origin story of not just our species and not just our planet, but the entire universe, to me, this is one of the greatest contributions to human civilization that I know about. And so this equation is the start of that. And so we like to show this picture. So what's the book about? Well, many of you probably have heard versions of the story. I know I thought I knew what happened in the period that we covered, but it turns out most of what you heard is not actually completely accurate. So the book covers the period from 1911 to 1922. For those of you who know something about solar eclipses and the role that Sir Arthur Eddington played in this story, you know that it was the eclipse in 1919 that we ascribe as having been the fundamental observational support that gives us confidence that the theory of general relativity is an accurate description of nature. So what as I said, in this book, we actually start, in fact, when we cover, so we're about eclipses. Let me just put that. That's the context of what the book is about. It's about the eclipses. It's about the astronomers who were pursuing these eclipses. It's about the adventures that they had pursuing these eclipses. And so we try to let them tell you their story with us as the intermediaries to bring this forward. In this map here, what I've done is I've traced out the paths of total eclipses from the period of 1900, when one actually crossed the southern United States, and we have stories about what it meant when the British astronomers came to places in Georgia and Alabama, and talk about a culture clash. All kinds of interesting things went on there, and so that's part of our storytelling. And of course, the final eclipse in this is the one in 1922, it turns out. That's the one that really nailed it, and we'll get a chance. I see at least one person shaking their head. That's the one that really nailed this business about the deflection of starlight, because even though you have heard that 1919 was the end of the story, it was not. So we do all of these eclipses. The book is actually dedicated to these individuals: William Wallace Campbell, Charles Dillon Perrine, Sir Arthur Eddington, the best known of these characters, Sir Frank Watson Dyson, in some sense his mentor and guardian, Charles Rundle Davidson, Andrew Claude de la Chauvoir Cromlin, Edwin Finley Freundlich, and I was told it was pronounced Edwin, not Edwin, and Edwin Turner Coddington. These are the 8 main characters that we follow over the course of the decade. And of course, there's this guy in the background, Albert Einstein, because after all, he's the person who sort of sets all of this in motion. So who are these people? Well, for those of you who may not be familiar, William Wallace Campbell was an astronomer. He lived from 1862 to 1938. He was an American astronomer and the director of the Lick Observatory from 1901 to 1930, and he specialized in spectroscopy. He is my personal hero in this story, quite frankly, because if you look at his life, you'll find out this is just an amazing individual, from killing snakes on Mount Hamilton as they are establishing the Lick Observatory, to hauling 100-pound packets of equipment off ships on Western Australia. This is William Wallace Campbell. He's just an amazing man. He went on to become the president of the University of California, Berkeley. He was also the president of the National Academy, if I remember correctly. Just an accomplished scientist. He's the kind of scientist I dream about becoming. Charles Dillon Perrine, an astronomer who had a very interesting story. He actually starts off as a devotee or a mentee of Campbell in the Lick Observatory, and then moves on to Argentina in an effort to establish the major Argentine National Observatory, and winds up spending the majority of his life there. It's somewhat a tragic life, but I'll talk a little bit more about that later. Sir Arthur Stanley Eddington, everyone's sort of heard of him, and certainly in this community you all know who this individual is. He was quite an amazing scientist, an astronomer, physicist, mathematician, philosopher, and popularizer of science, and he anticipated the discovery and mechanism of nuclear fusion as a process that powers a star in stars in his paper, The Internal Constitution of Stars. The other thing I would say about Eddington that I find him sort of just a delightful character is that he was also a pacifist. And someone mentioned that there's a book by Matthew Stanley that's out about now, and it talks about much more focus on Eddington's pacifism and the role that played in his going ahead and making the observations. Sir Frank Dyson, largely remembered for being an expert on timing. And for people who do astronomy, you know how important timing is if you're going to point your telescopes in the right direction. And he was actually one of the people who was on one of the two expeditions that Eddington basically headed. Charles Rundle Davidson. Davidson played an important sort of accidental role, because the main telescope that he was planning to make the measurements actually failed in terms of the conditions of the photographic plates that came back. And he had this backup telescope that he took with him on the suggestion of a Roman Catholic priest named Father Couturier. And this secondary telescope is the one that caught the images that Eddington used in making the argument that Einstein had gotten it right. Andrew Claude de la Charroy Cromlin, technically English, but as you might imagine from that name, an immigrant family from France, and his coming to work for Eddington is in fact initiated in some sense by the First World War. Because remember, I'm covering the period from 1911 to 1922. And in 1914 to 1918, the First World War, this horrendous, murderous period when about at least a third of the young manhood of Europe was slaughtered in this senseless conflict. Edwin Friendly Freundlich. Edwin is typically lost to history, but one of the most interesting things about this individual was that when Einstein finally figured out that light deflection was one of the things that could help him solidify his theory of gravitation, he needed astronomers, because he was certainly not an astronomer, and he hung out with people like me, physicists. What do we know about astronomy? He needed astronomers to come to his aid in order to get these measurements made. And he made appeals to groups of astronomers. And the first astronomer who took him seriously was Edwin Finlay Freundlich. It's sort of tragic that Finlay Freundlich's name is basically lost to history. Most people never have heard of all that he went through to support the idea of interesting the astronomical community in getting these measurements made. But it's a heroic story, and certainly he's one of our heroes in this. And then finally, Edwin Cottingham, again, a clockmaker. And in fact, his life actually ends with him on a clock tower. He went to repair a clock tower at a local church and winds up at an advanced age and actually succumbs to illness. But he was in love with clocks. So as that saying goes, he died doing what he loved. Here are these people. Here we see Campbell on the left and Perrine on the right, as young men. Here we have, on the right, we have Cottingham, and on the left, we have, why am I drawing a blank all of a sudden? I'm so sorry. Thank you, Dyson, indeed. Here we have Eddington. Here's Eddington and Dyson. I'll come back and get the name. And this is Edwin Friendly Freundlich, who I mentioned prominently. And this gentleman here is Davidson. So you'll notice I showed pictures of all these other people as young people. And I showed Davidson's picture as a relatively mature man. In fact, this picture was taken just a few years before he died. If we go back to the biographies, you'll notice that, where is it? That Davidson, where did I put you? There we go. Died in 1970. This is a particularly long-lived person. Has helped establish the coming of general relativity and lives long enough to see humans walk on the moon. One of the things that we found out from personal family communications, because I told you my co-author was a fantastic researcher, she was able to track down descendants. We found out that when the moon landings occurred, he was a skeptic. He said, surely they must have faked those pictures. And so this is what I mean by getting an inside look at who these people are as people, to actually see what they say and think, and that's what our book is about. So, back to a little bit of mathematics, because that's where people like me make our living. We know that our universe is one that has curvature, so we have a curvature tensor that's non-zero. We can classify the three different phases of possibilities with no curvature, lambda equals 0 being Minkowski space, lambda positive being de Sitter space, and lambda negative being anti-de Sitter space. And so this leads to the possibility of 5 different universes. There's some things in this picture that depend on the initial conditions of the Big Bang. So if lambda is equal to 0, and you have more energy that was confined to matter than to gravitational field, the universe would continue to expand forever. On the other hand, if at the instant of the Big Bang more energy was in the gravitational field, you would get an expansion for a while, but eventually the expansion would slow down, and you would expect a big crunch. If lambda is positive, the universe comes into existence, and it just grows. And that is apparently the one we live in. On the other hand, if lambda is negative, you could get, and this is the reason Einstein introduced the cosmological constant, was because if you don't introduce the cosmological constant, the universe, through the Friedmann-Robinson-Walker equations, does not admit static solutions. And so the universe always grows, and that's why he initially introduced the cosmological constant, was in fact to make sure that the universe was static and eternal, which was the consensus opinion of all the best cosmologists and astronomers in the world. I like to point out that if he had, this is very different from the Einstein we remember. So Einstein's remembered as a rebel. And if he had stuck by his guns, he would have not introduced the cosmological constant. He would have predicted the expansion of the universe. And then when Hubble discovered the expansion of the universe, he might have gotten a second Nobel Prize, right? So all of these things are things that one can surmise. So that's the science that is behind our book. But I wanted to do some readings from the book so that you get a sense of what it is that we've actually done in this document. As I said, it's not your standard book written by a physicist, because I didn't write it alone. We wanted to write a piece of literature. In other words, we wanted to realize an idea that I often hear, because people often talk about STEM, science, technology, engineering, mathematics, and then people say, but where's the A? Where's the art? Why isn't it STEAM as opposed to STEM? This book is really supposed to be a model for what a STEAM document would look like. It's our best attempt to produce such a thing. So I'm going to do some readings now from the book. So let's back up a little bit. So in 1915, Einstein does not have those equations that I showed you. He's playing around with various equations. One version of the equations is what we call scalar gravitation now, that was worked on by Gunnar Nordstrom, among other collaborators. Einstein was collaborating with people. He wasn't out there being a lone ranger out there trying to figure it all out by himself. He was talking to people. So one of his variants was to try scalar gravitation. Again, for those of you who studied some general relativity, you know that means that the metric is just a scale factor times the usual Minkowski metric. He also studied other variants, other things that we would now recognize as something closer to the theory of general relativity, but without understanding the proper way in the modern language of people like me of how to pick correct gauge choices for making calculations in the theories. And so in 1911, he thinks he's got a theory of gravitation. It's called the Entwurf theory, and that's Entwurf. It's his first theory of gravitation. And he uses this mathematical construct in order to make a prediction about the bending of starlight. Now, he's not the first person to have the concept that the light of stars grazing the sun will be bent. In fact, the first person who did that was Sir Isaac Newton himself. Isaac Newton speculated on how much the starlight would be bent. And his calculations basically went as follows, that if you could catch a starlight being bent near the limb of the sun, it would be bent through 85 to 87 arc seconds. Well, most of us don't think in terms of arc seconds. And so to translate that to numbers that everyone can understand, that's about the thickness of a dime seen at 1.7 miles away. So that would be the bending. So when Newton makes this prediction, no one can think about a technology that's going to actually detect such a bending. Interestingly enough, a German physicist by the name of Johann Soldner, around 1800, redoes the calculations and gets the same number. When Einstein makes his prediction in 1911 in his Entwurf theory, he also gets the same number, about 8.5 arc seconds. So he's got this prediction. I'm sorry, 0.85, sorry. Thank you, 0.85. I did it off by a digit there, but I'm a theorist, so, you know. So he makes this prediction. He needs to have astronomers go out and test this. He actually has some very interesting ideas. He was wondering, could you use Jupiter to measure this deflection? But eventually he becomes convinced that only eclipses will work. And so he begins to advocate in the community of astronomers to have people go out and make this measurement. And Edwin Trinley-Freundlich is the first person who takes up the challenge and says this is a serious problem for astronomers to do, and that we as a community should go out and actually do it. Now, among those paths of eclipses that I showed you, let me go back to those. Oops. There's one in 1914, the one that starts in northern Canada basically and crosses Europe, crosses into the zone of conflict where the war is being prosecuted in Europe. And there are several expeditions who were set out to measure, even though there was a war going on. They didn't know there was a war coming. They had planned for years earlier, but they set out to make this measurement. And two of them actually wind up in the Crimea. And neither one is able to make the measurement. One of them because they had bad reports on the weather, and they didn't understand how cloud formations worked around a particular mountain that was in the way. And the other one because of basically military intrusions. And in fact, the second team is actually, part of them they are incarcerated by the Ukrainians. And so their equipment is confiscated. Even their maid is put in jail. And she's a German lady who has lived there for several decades, and yet she was considered an enemy spy by the officials at that point. These are all stories that we've dug into. And so, if history had been a little bit different, one or both of those expeditions would have made the measurement. And if they made the measurement, the number would have been twice as large as a prediction of Albert Einstein. So we have a passage in our book where we want our readers to consider what's the role of luck in a scientific discovery of this magnitude. What if clouds hadn't covered the sky over Campbell's rented dacha near Kiev during the eclipse of 1914? What if, after young Kenneth Campbell shouted, "Go!" the Lick Observatory plates had caught perfect images of the stars and would have finally revealed an answer to Isaac Newton's question, do not bodies act upon light at a distance and by their action bend its rays? Yes, they do. What if Freundlich had not been a prisoner in the Crimea? What if he and Perrine had risen to the bright sun and cloudless skies over the hillside vineyard? Better yet, what if Frank Dyson had answered Freundlich's letter of 1913 with a different response because Dyson had turned down support for another expedition? Instead of no, but if the Astronomer Royal had agreed to have Charles Davidson test for light deflection in Minsk in 1914, which is also under discussion. Davidson would have had clear skies and perfect images on that date. The observation would have been extraordinarily successful. Because nature never makes errors in her calculations, human beings would have been held accountable. If measured and read correctly, the universe would have gladly given up the right answer, about 1.7 arc seconds. Newton, the genius of classical physics, would have been mistaken. Einstein, the genius of modern physics, would have botched his calculations. This would have been our first notice of this guy, Albert Einstein. He's the guy who couldn't get the right answer when it came to deflecting starlight. After all, both of them had played a minor role in opening the door to the cosmos, but it was as if if for the first 200 years physicists had watched a man wearing a hat walk into a room and then saw the hat blow off his head over and over again. What was causing that to happen? Newton couldn't actually tell us. If you read the Principia, Newton's very clear that action at a distance for someone who thinks very deeply about it is not an acceptable solution. And Einstein had figured out that, well, he got the wrong answer too. But in his case, it's a very deep misunderstanding of how to calculate the corrections correctly. So what is that? What's that message for my students? Because that's one of the passages I want my students to understand. Well, when you're thinking about this guy, Albert Einstein, that you hear is the world's most perfect genius, his first major prediction on starlight is wrong. Just like you got your homework wrong. So it's not a terrible disaster not to always get your homework right. If you keep working at it, you might get the right answer later. And I think this is a very important thing for students to understand, as opposed to going out and feeling as if there's no chance for them to become, him or her, to become a great scientist. And so we saw stories like this throughout the text to show the humanity of our 8 astronomer heroes as they pursue this measurement. Another passage that I'd like to bring to your attention is actually our opening passage. As I said, it was my dream for this book to be very lyrical and poetic, and I know that I'm not capable of doing that. But someone like Kathy is, and so the opening epilogue of our book reads as follows. I must search in the stars for what is denied me on earth. Albert Einstein. You are standing in the path of totality, waiting for a total eclipse of the sun. You have never witnessed one before, but each is different. It happens slowly, as if giving your brain time to prepare as the shadow of the new moon speeds forward to devour our closest star. At first contact, it looks as if a dark mouth has taken a bite of yellow from the sun. But this is still your world, the one you have known all your life. The bite grows larger as more of the sun disappears. With 10 minutes to second contact, the total eclipse, daylight has gradually slipped away, replaced by a bluish twilight. The once magnificent sun has been eaten down to a thin crescent. Familiar landmarks now exist in a world of monochrome color you do not recognize. Odder things begin to happen. Reflected through the leaves of nearby trees, thousands of small images of the sun's crescent are spilled on the ground in confusion. Cows herd into the barn. Nighttime insects rattle in the surprise. Diurnal flowers fold their petals. A shivering dampness flows over you. At your feet, the grass has turned to silver. This goes on for quite a bit, but it's basically it is non-rhyming poetry, because it's an attempt to express what people feel when they see their first total eclipse. And I think Kathy has done a wonderful job of rendering in words what it's like, and we hope that our readers will pick up this part of the text and get excited about what comes next. The other thing that we've done in this book, although I told you we concentrated on the period from 1900, we actually do much more, because it turns out that eclipse watching actually was part of establishing science here in America. Some of our first national expeditions created by this country, even before it was a country, was to go watch the eclipse that occurred in St. John's, Newfoundland, before the Constitution. So eclipses have played a role in American science before there was an America. Another of my favorite passages. This is on page 25. It's in a section called Secrets of a Gravel Sorter, and the gravel sorter we're talking about is Albert Einstein. That Albert Einstein was much more enigmatic than the world realized is a detail that almost escapes the world notice. He kept a universe of personal secrets within his head, along with all that brilliance. Most amazing about the marriage. The most amazing about marriages. Why can't I say that word? Maritek's premarital pregnancy, or Liesel's birth. Einstein had a child before he was married to his first wife. The child never lived with them. They lived with their maternal grandparents. And then the thing that's really interesting is that no one knew about the child until 30 years after Albert Einstein died. He died in 1955. It wasn't until 1985 that documentations of this child's life came to existence. It was found in a very remarkable manner because Mileva, his first wife, kept letters in a box for over 50 years from her young experience of being a newlywed, and even pre-newlywed in this case. And her daughter found these bound letters in a closet after her mother died, and that's how we know about this. So this is part of the collection at Caltech. The packet had been bound with a worn ribbon. It appeared that for 50 years it had been saved. Given the many turbulent years in Albert Einstein's personal life as he conceptualized ideas that would change the world of physics, it's astounding that he accomplished anything at all. But other scientists before and after Einstein have utilized emotional turmoil to fuel their productivity, and Einstein had it in spades. Whatever happened to Liesel has been a subject of speculation for years. The letters back and forth between her parents, Mileva's parents, at least those that still exist, do not say whether the child died or was adopted. They only speak of the birth at her maternal grandparents' home in Novi Sad, Serbia, of Mileva's difficulty in delivering the baby, and the child's illness from scarlet fever. Albert showed concern for his daughter, at least in his letters. I love her so, and I don't even know her yet. Couldn't she be photographed once? Couldn't she be photographed once she is totally healthy again? Will she be able to turn her eyes towards something? He enjoyed writing about Liesel, but visiting her seemed less attractive. It is as if she was another thought experiment. So one of the things that we discovered in our research has to do with this eclipse in 1902. There's a lot of indications that that's probably, if not the day, around the day that Liesl died, because it looks as though the child died. And so even though Albert Einstein never recognized the existence of his daughter, it is as if our universe did. And this is part of the mystery of this place that we live in. Albert Einstein himself in his later years commented that the universe is a place of mystery. And so to me it is sort of appropriate that perhaps in some mysterious way this child was recognized, if not by her father, maybe by the universe. I'm next going to talk about my hero of the book, as I mentioned that earlier. William Wallace Campbell is the person I most admire after having produced this book. And I'm going to do an extended read about his life. I belong on the mountaintop. When William Wallace Campbell arrived back in San Francisco from the 1922 eclipse expedition, it was the month of December. His steamer sailed into the port of San Francisco, where an unlikely delegation was waiting on the dock. The welcomers were the University of California regents, who insisted that Campbell accept the presidency of the university. They needed a man with vision, with executive and administrative skills, and, as one of the deputation put it, a man with backbone. Campbell had been offered this prestigious position before and had turned it down. He liked his life on Mount Hamilton and his work studying the stars. He was now a world-renowned astronomer with all the impressive medals that could possibly be awarded, along with many honorary degrees. He had already served as the president of the American Association for the Advancement of Science, as well as the Astronomical Society of the Pacific. And for those of you who are not on the history of the Astronomical Society of the Pacific, they played an enormous role in strengthening America's entry into world-class astronomy. For 3 years more, he was the president of the International Astronomical Union and the American Astronomical Society. As director of LIC, he couldn't have been busier. But the regents reminded him that they had always met his past requests for the mountaintop community and observatory. Perhaps now was a time for him to help the university. They persuaded him by consenting to his request, the primary one being that he would retain the directorship of the observatory, and second, the regents would not interfere in the university's internal matters. The Campbells could retain tenancy of the house on Mount Hamilton, where they had raised their sons. It would now be expanded and remodeled, and where they might occasionally find solitude or entertain friends. Planning on a short term of service, President Campbell began his new role next July at the age of 60, assuming the presidency of the university. Now remember, this is 1922, so it's not like these days where we think that 60 is the new 40. Right? You hear that all the time, 60 is the new 40. This is back when 60 was the new 60. So he took leave of absences in September. He and his wife Elizabeth traveled south the border to New Mexico for a journey. They were able to raise donations from the likes of the Hearst, the Rockefellers, and others. This was Berkeley's ascent to being one of America's greatest universities. This goes on for a while, but let me get to the point where I think the true measure of this man lies. In 1935, his term with the Academy finished. He and Elizabeth returned to California. He was now 73 years old. He had likely suffered a stroke, for he was diagnosed with aphasia, a condition caused by the damage of those parts of the brain that deal with language and communication. After a short visit to Mount Hamilton, perhaps to say goodbye, the Campbells moved into a charming apartment in San Francisco. Its windows looked out on the blue waters of the Golden Gate. The famous bridge had been under construction for 2 years before the Campbells returned to California. It would be finished and open to traffic 2 years later in May of '37. While visitors to their home found the couple in good spirits, the famous astronomer's health was now declining rapidly as aphasia took its toll. Once so elegant, Campbell struggled to find the proper words. Even reading and writing had become laborious. The eyesight in his remaining eye was also failing. The astronomical study that had been his passion for so many years in that heavenly classroom filled with stars was now lost to him. On June 14, 1938, while Elizabeth slept, he rose before dawn to carry out the plan he had conceived. Apologizing for his poor handwriting, his scribbled words were incoherent in places, the man known as Wallace to family and friends wrote 5 heartfelt notes. The last at 4 in the morning. He praised his wife and sons, his greatest pride, and thanked his friends. His foremost worry was not wanting to be a burden to his wife. Goodbye, dearest Elizabeth. Be of great courage, was perhaps the most difficult thing to write. It is better that I go away now, with my powers nearly all gone, than to stay and become an incompetent person. He committed suicide, leaping from the third story high room. So this is a man that cared deeply about science, cared deeply about his family, and was not willing to put them through the struggles that he foresaw in the remaining part of his life. I admire that kind of strength in people. And that's part of the reason, but only a small part of the reason, why for me personally, William Wallace Campbell is the hero of this story. Because it was his fortitude and determination that drove the development of astronomy in this country. It raised Berkeley to near pinnacles of being one of the greatest universities in the country. And it also is illustrated in his 1922 expedition. If you look at our map, you'll see that there was an eclipse in June of 1918. So that's before the spring eclipse in 1919. And in fact, there was an attempt to measure the deflection of starlight at a place called Goldenrod, Washington. And Campbell was one of the people who wanted to make that measurement. You will remember earlier in the story I talked about the fact that the expedition to the Crimea had its equipment impounded by the government. That equipment remained in Russia for years, but Campbell was very persistent because it was his equipment. And so he would work through agents. And so it's very interesting that in his attempt to get the equipment, it traveled from the Crimea to Moscow, from Moscow to Novosibirsk on the Trans-Siberian Railroad, and ultimately to the west coast of Russia because he was trying to get his equipment back. And if the timing had worked, because this is what he was working to do, if the timing had worked, he would have had that equipment for this June 8th, 1918 eclipse in Goldenrod, Washington. And he might well have been the person who had the first definitive measure of the deflection of starlight by our sun during an eclipse. And it would be he, not Eddington, that we would be talking about and that the public would talk about as the person who lifted Einstein up to worldwide fame. And so once again, it shows the precariousness of what research is actually like. As a researcher, you can work as hard as you possibly can, but the best thing that you can do is hope that A, you're right, and that B, the universe will be congenial to your discovery. And this is a very strange state. This is something Einstein himself commented about, by the way. He said, the life of a theorist is not to be envied. And the reason? paraphrasing, is because for theorists, the final arbiter is nature, and nature is a very, very tough judge. She doesn't say yes or no. She usually says no. And that's usually shortly after the prediction is made. However, when she doesn't say no, the best she does is say maybe. And so we never get an affirmation from nature. What we get is a conditional acceptance. So, again, this means that if you're a student and you want to work hard, it's not guaranteed. It wasn't guaranteed to Albert Einstein. It wasn't guaranteed to Eddington. But follow your passion. Be like Campbell. Be diligent. Work hard. Become the best scientist that you can become. And then live in the hope that the universe will be congenial to you making a discovery. And that's the kind of reason I wanted to write this book. Thank you.
Thank you, Jim. Fascinating. Let me start off with just a brief question. You mentioned that it was the eclipse of 1922 that was really definitive. Is this just a question of error bars, of nailing that precise deflection?
So the point was that in the 1919 discovery, or rather observations, there were two sites, one off the west coast of Africa, one in Sobral, Brazil, and at both sites they had problems with photographic plates and the temperature. And so a number of the plates that were actually made were not used when Eddington analyzed the plates for the light deflection. And because of that, many people, even to this day, say that Eddington cooked the books because he didn't use all of his data set in order to go ahead and make the announcement before a photograph of Sir Isaac Newton, where he apologized and said, this kid, effectively said, this kid Einstein is right, you're wrong. So that was part of the equipment that Campbell took on the 22 expedition had none of these problems. It was improved. It was 4 years later. It was improved. And so there was no question about the correctness of the plates that came back.
Question?
I have two questions, actually. One is you mentioned that Newton actually calculated deflection of light according to his theory.
Right.
I had never heard that before. I had heard that the first such calculation using Newton's theory was in 1802.
By Solvent.
Yeah.
Yeah. But in fact,
I was curious, where can I find?
I'll have to look in our notes because we actually have tabulated such things. I don't remember right offhand.
The other question I had is on the 1918 eclipse.
Yes, and goldenrod, yes.
What were the stars visible during that eclipse? Was it nearly so favorable as the stars and the Hyades that were visible in the 1919 eclipse?
I'm going to say I don't know the answer to that question. If you will send me email, I will certainly track that down. Thank you for the questions. There's a hand in back.
Have you experienced a total eclipse yourself, and what was it like?
Not a total eclipse. I only partials. That was scary enough.
Charles.
At the time, was the result from the 22 eclipse recognized as definitive? Or was it thought, okay, it's just nice that they redid what they did?
No. Well, it was recognized as definitive in the astronomical community. The general public is almost totally unaware because all they heard was Eddington, Einstein, 1919, and they thought that was the end of the story. But in the astronomical community, it was well known that there were lots of questions. There were a lot of people who were not satisfied with the role that Eddington, and Eddington, Eddington did not act in subterfuge. I mean, he gave very clear statements about what he was doing in his analysis, and he also stated why he was doing it. And I tell people that I'm a theorist, so I'm really terrible in the laboratory, but I have an enormous amount of respect for people who do observation and experiment, and I have understood, even as a theorist, that when you are practicing your art at the highest level as someone who does either observation or experiment, there's a part of you that you may not be able to explain in logical thought. I call it expertise. One example of expertise, and it's slightly removed, but one example of expertise is, I don't know how many of you saw that movie Sullenberg, but there's a scene in Sullenberg. Sully was the pilot who landed this plane on the Hudson and saved everyone on board. But there's a scene in the movie where Sully says, "I felt it go." And he was talking about the functioning of an engine. And he said that with absolute certainty. And that's what expertise allows you to do. It's not that you can necessarily logically justify what what it is that causes you to make decisions. But expertise is the thing that allows us, in some sense, to tap into our intuition. And Eddington's intuition was right, that these plates were just not trustworthy, the ones he didn't use. Yes, sir.
What do you think of this idea that Eddington got involved in this because it was sort of his being a pacifist and wanted to reconcile the German, English?
So there's a book by Matthew Stanley that I understand was Matthew here?
No, it was Avi Loeb
Okay.
was taught Matthew, took an undergraduate course here.
Right. So there's this book by Matthew Stanley. I'm not going to say that he got it wrong, but I am not convinced. That's the best thing I can tell you. As I read Eddington's life, because that's something I worried about for 3 years or so, I don't think he would be swayed, quite frankly, by his pacifism and wanting to heal the world. As far as I can tell, he's exactly what you are, a dedicated scientist looking to get the best answer he's capable of producing.
I have a question regarding the final part of your talk on the nature saying no.
Yes.
A few months ago, I spoke to a young fellow in Russia doing theoretical particle physics, just graduated as with master's degree, and he told me that in their group, which is pretty famous in Russia and abroad, the young generation doesn't want to work on anything that can be proven right or wrong within the next 5 years. They say it's not sexy enough. We want to do something that cannot be proven at least for at least 50 years. What would be your take on this?
So even though I have spent my entire 40 years in science working on supersymmetry, which is a pretty speculative idea, I think I didn't choose, that was not the reason that drove me to do it. I tell people that as I understand the nature of science, the only thing that stops us from being a faith-based operation is that we are willing to be educated by nature. That means that at the end of the day, observation experiments are what ground our belief system, which is very different from most belief systems. In fact, this is the philosopher Kurt Popper, in fact, uses this as a definition of what is science. Kurt Popper basically says that if you have a system of belief, unless it has internal mechanisms that allow it to be falsified, it is not science. And so that may be sexy to work on things that are not going to be proven right or wrong in 50 years or so. That's not, so I have 2 children that are going to be, looks like they're going to become physicists. If they came and told me that, I'd be upset.
Another question. You described to us how Einstein got the answer incorrectly
Yes.
in 1911.
Yes.
And he's later, of course, famously said that the cosmological constant was his biggest blunder.
Yeah.
All of which, reveals a side of a person that understands that nature bats last. And yet, I don't know if the quote is correct, and I'll butcher it, but supposedly when he was told of the results of the 1919 expedition,
Yes.
and that it agreed with his theory,
Yes.
his response was something along the lines of course, it agrees. I should feel sorry for God.
For the good Lord.
For the good Lord. If it wasn't, the
That's right.
theory is right.
That's right.
Exclamation
No,
point.
that's the quote, and you did pretty well. I mean, you can find it in many places. Walter Isaacson, in his book, has this particular quote also. And Walter is a thorough author, so he's one of the people I trust implicitly in these sorts of things. But you're right. But to me, this reveals the kind of duality that those of us who take on the mantle of science have to have. Because if you don't have the confidence that some crazy idea that could just change our nature and further our understanding of how Mother Nature works, if you don't have absolute confidence in that, you're probably not going to persevere to get it to happen. And then, look, maybe nature will, at the end of the day, say, I'm sorry, kid, you got it wrong. But you got to have that confidence. So that's how I resolve it.
Yes, sir.
Well, just contrary to that, I heard that he was very anxious to learn the results of the eclipse expedition, which is somewhat at odds.
Right.
No, that's also true as far as we can tell. So he was contradictory even on that.
Let me remind people that if you found Jim's talk fascinating, as I did, the book upon which it's based is being sold in the back of the auditorium, and I don't know if you're willing to sign books that people get. I don't want to speak for you, but in any case, you can read more about it back there. If there are no other questions, let's thank Jim again. Oh.
But raising the money probably is not easier than it was before.